The topic today, differential equations, growth and decay, corresponds with section 6.2 in the textbook. What we're going to see today kind of blends over from the previous section with the separation of variables and solving a differential equation. So y prime, or dy dx, remember, is the slope. So the slope is given by 2x over y. We want to get back to our original equation. First step, separation of variables. Get the x's and the dx's together, and then also get the y's and the dy's together. So to do that, we need to take the y prime, just write it as dy dx like it is. Tried to think of another word and I blanked, so like it is. And we want to get the x's and dx's together. So multiply both sides by dx. That will cancel the dx's on the left side. We also want to get the y's and dy's together. So multiply y, multiply by y. So on the right side, the y's will cancel out. Then we can rewrite the equation, kind of tighten it up a little bit. So y dy equals 2x dx. And now we can anti-differentiate. So bring that up here, kind of running out of room. And y dy and the differentiate becomes 1/2 y squared. And 2x dx becomes x squared plus c. Now we're going to solve for y. So multiply everything by 2, y squared becomes 2x plus just c again, because c is some number times 2, again is some number. And then square root. Y becomes, now these are differential equations, not differential functions. So equations, when you square root, plus minus. And you have to put the plus and minus in there for the equation. But either the plus or minus will be determined if you have a c value. Or sorry, not a c value, an initial condition. So for the differential equation, plus minus, do that. Then, with an initial condition, you can decide, is it positive or negative? We'll see a lot more of those examples throughout the unit. But growth and decay. So rate of change. So we're looking at rate of change of the variable y. We're looking for these words, directly proportional. Rate of change is directly proportional to the value of y. So we're looking for that directly proportional right there, the k value. So rate of change of y, dy dt, is equals proportional to y. They're directly proportional, the k value. Now this is dy dt, a differential equation. And this leads us to our exponential growth and decay model. Y equals c times z to the kt. Note we have the k there. C is the initial condition, initial value of our exponential growth and decay model. And a lot of times when we solve this and we use this equation, a lot of times there's very little calculus in the problem. It is a lot of algebra. Let's walk through an example, okay? So the rate of change of y is proportional to y. So we have that language, the rate of change is proportional. So y equals c times e to the power of kt. When t equals 0, y equals 2. That's an initial condition. When t equals 2, y equals 4. Another initial condition. What is the value of y when t equals 3? So let's start. We have initial conditions. We'll start with the first one, 0, 2. You see me kind of peeking over in my notes, just making sure I write it down correctly. So 2 is my initial y value, equals c e to the k times t, which in this case is 0 from our initial condition. So anything to the 0 is 1. So c equals 2. Now let's use the next initial condition, 2, 4. So 4 equals, c is 2, e to the k times 2 again, because 2 from the initial condition to 2, 4. So divide by 2, so 2 equals e to the 2k. The inverse of e is ln, so to get rid of e, take ln of both sides. So we have ln of 2 equals 2k, and k equals 1/2 ln of 2. So now we have a solution for c and a solution for k. It's a better row, okay. So we want to know what the value of y is when t equals 3. So c is 2. Sorry, what do I see? I said it, I didn't write it. E to the 1/2 ln of 2. And t is going to be 3. So our model, so when t equals 3, go ahead to plug the 3 in. So y equals 2e 1/2 ln of 2 times 3. And the simple simplification, 1/2 and 3. 3/2 ln of 2. See, look at that. No calculus involved, just a lot of algebra using initial conditions and e's, inverse of e's, ln's. Alright? So the differential equations at the top, we're going to see a lot more of those. The growth and decay, it's good to know, it comes up from time to time. Just looking for that language, the rate of change of y is proportional to y. Directly proportional gives the CE to the KT.